Welcome back to Calculus 2. We are continuing learning about Taylor and Maclaurin series. And we actually have a different handout here, and we're sort of switching gears from what we did with the previous handout. In the previous several videos, we were really trying to understand the concept of Taylor and Maclaurin series, see where the formulas for those expressions came from, and then practice finding Taylor and Maclaurin series from start to finish. Our goal for the examples on this handout is not so much to come up with Maclaurin series from scratch, but rather to use Maclaurin series to solve certain problems. And here are the sorts of problems that we're going to solve. We can use Maclaurin series to do the following things. Well, in some instances, we can use a Maclaurin series to find the Maclaurin series for a related function. We actually saw this with sine and cosine. We found the Maclaurin series for sine completely from scratch by hand. But then we didn't do that for cosine. We found the Maclaurin series for cosine by taking the derivative of the Maclaurin series for sine, because the derivative of sine is cosine. So we'll see that sort of a concept, using a known Maclaurin series to find the Maclaurin series for a related function. Another application that we'll see for Maclaurin series is to find the sum of certain series. So far, there's only been really one kind of example where we've actually found the sum of an infinite series. That was convergent geometric series. What we're going to do here is take a non-power series and recognize it as a Maclaurin series where there's been some number inputted for x, and we'll be able to find the sum of certain series that way. Finally, we'll use Maclaurin series to solve calculus problems, such as limits and integrals. Before we actually work through any examples, I want to show you the breakdown of these examples based on what sorts of problems they are that we just listed out. So examples 1 through 5, we're going to be taking a known Maclaurin series to find the Maclaurin series for a related function. So these examples, we will use a known Maclaurin series to find the Maclaurin series for a related function. In examples 6 and 7, we're going to use a Maclaurin series with a specific value of x to find the exact sum of these different series. These are not power series because there's no variable x, and it turns out that both of these series will converge to a certain number. They are not power series, they are not geometric series, but we can still use Maclaurin series to find the sum of these two specific series. In examples 8 and 9, we're going to use Maclaurin series to find integrals. In examples 10 and 11, we'll use Maclaurin series to solve limits. Example 12 doesn't necessarily fall under any of these different categories, but it's possibly the coolest problem in all of Calc 2. We're going to see some incredibly beautiful mathematics from example 12. You definitely don't want to miss that. So here's the breakdown of the different problem types that we're going to solve in this section. And we'll use these different Maclaurin series. So here on the front of the handout, we have different series listed for different functions. And for each one, we have the radius of convergence. So this series should look familiar. This is a geometric series, yes, but it's also a power series. And this power series converges to 1 over 1 minus x, as long as we're within a radius of 1 around 0. Here's the Maclaurin series for e to the x. We found this. The radius of convergence here is infinity. We found the Maclaurin series for sine. There it is. This also has an infinite radius of convergence. So does cosine. We didn't look at arctangent, but arctangent has this Maclaurin series. Natural log of 1 plus x, centered at 0. Here's the Maclaurin series for that. Then finally, this is the binomial series, which we looked at in the last video. It's important to have a strong working knowledge of these Maclaurin series and their radii of convergences. We want to know both the closed form expression with the summation notation, and we want to know what the series look like expanded out. So for each one of these, we want to be very familiar with the form so that we can use them easily. We're going to practice using these different Maclaurin series to solve these types of problems in this section. Let's begin with example 1. We want to find the Maclaurin series for x times e to the x. We're going to use a Maclaurin series that we already know about. We're not going to do this by hand from scratch. We're going to leverage our knowledge of a known Maclaurin series to find the Maclaurin series for x times e to the x. Which Maclaurin series do you think we'll use? Probably the Maclaurin series for e to the x. Let's see how this works. Our function here is x times e to the x. And we want to write down the Maclaurin series for e to the x, since this function involves e to the x. So let's just write off to the side here. The Maclaurin series for e to the x, this is the sum, n starts at 0, goes to infinity, of x to the n divided by n factorial. So in my original expression, I can just replace the e to the x with this summation. So I have x times the sum from n equals 0 to infinity of x to the n over n factorial. I'm just literally replacing e to the x with its Maclaurin series. Now I have x times a sum. This is a whole bunch of things added together, and I can distribute the x inside the sum. So I can write this as the sum of x times x to the n over n factorial. I'm just distributing the x into the sum. I can think of a whole bunch of things being added up here, and I'm distributing the x, multiplying it by all of the terms. So this is what I get. Let's take one more step to simplify. X to the first times x to the n using rules of exponents. That is x to the n plus 1. We still are dividing by n factorial, and there we have it. That is the Maclaurin series for x times e to the x. We could solve this from scratch by hand, making a table of the derivative values, plugging in 0, and we'd get the same exact expression. But it's much, much, much faster to leverage our knowledge of the Maclaurin series for e to the x to find the Maclaurin series for this related function. Let's solve example 2. For example 2, we're going to use a known Maclaurin series to find the Maclaurin series for the function f of x equals 2x times the natural log of 1 plus x squared divided by 3. What we're going to use here is the Maclaurin series for the log function, natural log of 1 plus x. If we look on the front page of the handout, we will see the Maclaurin series for natural log of 1 plus x. That's what we'll use to get the Maclaurin series for this related function. So for example 2, we're going to just first copy down our function. Our function is f of x equals 2x times the natural log of 1 plus x squared divided by 3. We see the natural log function, natural log of 1 plus something. So let's write out the Maclaurin series for natural log of 1 plus x. We can find this on the front page of the handout. The Maclaurin series for natural log of 1 plus x, using the information from the front of the handout, is natural log 1 plus x equals the sum, and goes from 1 to infinity, of negative 1 to the n minus 1 times x to the n divided by n. It's a really good idea to actually work through this problem on your own. Sit down and work through all the steps to find the Maclaurin series for natural log of 1 plus x, and you'll see that it equals this expression here. But for this problem, we don't have to do that. We're just going to use the information that we have for the Maclaurin series for natural log of 1 plus x to find the Maclaurin series for this related function. We're going to start by thinking of replacing the x with x squared divided by 3. So the natural log here is natural log of 1 plus x squared divided by 3. For the Maclaurin series that we've got here, we're just going to replace the x with x squared divided by 3. Let's go ahead and do that. We have natural log of 1 plus x squared divided by 3. I'm just going to write out the Maclaurin series for natural log of x, 1 plus x, but then replace the x with x squared divided by 3. So instead of having x to the n over n, like we have here, I replace the x with x squared divided by 3. So this right here is natural log of 1 plus x squared divided by 3, using this Maclaurin series for natural log of 1 plus x. I still need to write the 2x out front. So there's still a 2x out front here. I could leave the answer just like this, but I want to simplify a little bit more. I'm going to distribute the 2x into this summation, just like we did in the previous example. So we'll have the sum, n goes from 1 to infinity, of negative 1 to the n minus 1, times 2x. I'm just going to bring this 2x in right there. And then I want to expand out this x squared over 3 to the n. Using rules of exponents, this is equal to x to the 2n divided by 3 to the n. And I'm just going to put that right in the denominator. So I already have n in the denominator, and I'm going to put 3 to the n. So this x to the 2n, this comes from x squared to the n. 3 to the n, this comes from the 3 in the denominator here, raised to the n power. I can take one more step to simplify by combining the x times x to the 2n. I have the same base, so I can just add the exponents together. This is x to the first times x to the 2n, so that turns into x to the 2n plus 1. So my final answer here is the sum from 1 to infinity of negative 1 to the n minus 1, 2 times x to the 2n plus 1, divided by n times 3 to the n. Here is the Maclaurin series for the function 2x times the natural log of 1 plus x squared divided by 3. Finding this by hand from scratch using the definition of the Maclaurin series would be incredibly difficult. This would get very complex very quickly, and it would be really tough to predict the pattern that we see here. But using the Maclaurin series for the related function natural log of 1 plus x, we still have a couple messy steps of algebra, but we can get to the answer much more quickly.